Welcome all of you. So earlier we finished the portion of solar radiation, solar geometry and solar thermal, where we looked at concentrated solar thermal power plant and its components and a case study. So from now on, we'll go to the other part of the solar energy, that is solar photovoltaic. So in today's lecture, we'll cover some basics about what's the energy gap model, and the classification of materials based on energy gap, and the PN junction, which is like the foundational diode of any solar PV cell, photovoltaic effect, and what is a solar or photovoltaic cell. So energy gap or energy gap model, it is actually based on the band gap or the energy gap between valence band and the conduction band. So it is the range of energy where no electron states can exist. There are no electrons in that gap between the valence and conduction band. So you have here valence band, this is the conduction band, and that's the energy level of both the bands. So as you can see, valence band is at the lower energy level, conduction band is at the higher energy level. Between these two energy levels, there is a forbidden zone or forbidden energy gap where there exists no electron. So it is this forbidden zone between the top of the valence band, that is this point, which is always filled with electrons, and the bottom of the conduction band, which is either empty or partially filled with electrons. So this gap is called as energy gap or sometimes called as band gap. And valence band, as you can see here, it exists at lower energy level, but it has the highest range of electron energies which are normally present at absolute zero temperature, which is 0 Kelvin. So what happens in the valence band, the electrons are they are bound to the individual atoms very strongly, and they are not able to move freely through the crystal lattice of the semiconductor or of the material. So the electrons in this valence band, they do not contribute to the electric current. Okay, though the electron energies are high, the entire band is at a lower energy level, because it's obvious, like electrons, they prefer to stay at lower energy states. And in the conduction band, you can see the range of energies where electrons are delocalized, they are scattered and they are free to move, which enables them to carry the electric current. So it is the electrons in the conduction band which are actually responsible for movement of the electric current, and the gap between these two bands represents a barrier that electrons must overcome, and this barrier can be due to thermal, optical or electrical energy. And once they overcome this barrier, they can move from valence band to conduction band, and once they go in conduction band, then they are able to get delocalized or move, generating electric current. So that's the energy gap model, and using this energy gap model, we can classify the materials into three different types, okay, based on the structure of the band. When I say structure, it mainly focus on the size or the width of the energy gap or the band gap. So the three types of materials are conductor, semiconductor and insulators. So you can see in conductor, this is a valence band which is full of electrons, this is conduction band, and there is no band gap. The conduction band is actually overlapping with the valence band. So when there is a overlapping of two bands, electrons can easily flow freely. So those materials are called as conductor. If there is a huge band gap, like say wide band gap, more than 5 electron volt or sometimes up to 10 electron volts or even higher. So in such cases, it is not possible for electrons in this valence band to go to this conduction band because of the huge band gap or energy gap. So those kind of materials are called as insulators. Okay, there are no electrons in the conduction band. And semiconductors are those which has an energy gap in between, actually a narrow energy gap or narrow band gap in the range of 1 electron volt. It can vary from 0.7 to 1.4, 1.5 I guess. So you can see from valence band in conduction band, there will be some electrons in the conduction band which are responsible for carrying the current, and the gap between these two bands is in the range of 1 electron volt. So those materials are called as semiconductors. So this is the importance of energy gap and energy gap model, because it can help us classify the materials into conductors, insulators and semiconductors. So just taking forward the discussion, as we saw in the picture, conductors are characterized by overlapping valence and conduction band. They allow free movement of electrons, and they typically have 1 to 3 valence electrons in their shell, and they exhibit very low electrical resistance. Because they have low electrical resistance, they can ensure more flow of current, and examples are silver, copper, aluminium. So most of the metals, they are good conductors of electricity. Insulators, they have a wide energy gap, 5 to 10 plus electron volt, and this huge energy gap, it prevents the electrons from reaching the conduction band, and all the electrons stay only in the valence band, where their energies are very high, but then the entire band is at a very low energy level and it's not responsible for generating electric current. So they have a very high resistance, and examples are rubber, glass, drywood, all these materials which act as insulators, and they make electrical conduction impossible under normal conditions. The third type of material, semiconductors, they have a narrow energy gap, range from 0.7 to 1.4 electron volt, and their conductivity is intermediate and resistance is medium to high. Examples of semiconductors, the world famous, the most widely used in the solar PV cells is silicon, because it is one of the most abundant elements in the earth's crust. So silicon, germanium, gallium arsenide. So these are the semiconductors which have a narrow energy gap in the range of 0.7 to 1.4, and it is this kind of material, the semiconductors, which are often used for manufacturing solar cells or PV cells. So the next topic that we would like to cover here is PN junction, but before going to PN junction, let's look at what is P-type material and what is N-type material, and then how we connect them to form a PN junction, and how that PN junction is a fundamental foundational part of any solar or PV cell. You can see in the picture, this is a N-type semiconductor, this is a P-type semiconductor. Semiconductor is a silicon here, right? And here you can see there is one donor impurity which is contributing free electrons. For example, antimony, Sb is antimony, and P-type semiconductor it's boron. So it's like a trivalent atom, and here it's like a pentavalent. So a N-type semiconductor is obtained by adding a pentavalent impurity. So those impurities or those elements will have 5 valence electrons in them. So those elements having 5 valence electrons are called as pentavalent. So this pentavalent, like atoms of phosphorus, arsenic, antimony, when they are added to a N-types, to a semiconductor like silicon or germanium, then we can get a N-type semiconductor. So because it is these impurity atoms which will contribute one extra free electron, and this extra free electron will lead to formation of N-type semiconductor. Majority carriers in N-type material would be electrons and minority carriers would be holes, because once the electron jumps from its band and leaves its position, a hole is created in that place. So majority carriers in N-type semiconductors are electrons, minority carriers are holes. A P-type semiconductor, it is obtained by adding a trivalent impurity like boron, aluminium, gallium, indium. These are all the elements which has 3 valence electrons in its shell, and when these are added or doped with silicon or germanium, they can form P-type semiconductor, and these impurities contribute one extra hole, or they result in deficiency of 1 electron. So these impurity atoms create a deficiency of 1 electron called as hole. So in this case, majority carriers are holes and minority carriers are electrons. So those are the n-type material and p-type material, right? Now, when we connect them, we can get a p-n junction. This is unbiased p-n junction, where you can see a p-type material is attached to a n-type material, and then there is a depletion region in between. N-type material has lot of free electrons and p-type material has lot of empty holes. It is in this depletion region where the exchange of these charge carriers take place. So p-n junction, it is a boundary or a interface between two types of semiconductor material. One is p-type and other is n-type. P-type is often connected to a positive and n-type is often connected to the negative inside a single crystal of semiconductor. Okay, and it is the fundamental building block of diodes, transistors as well as solar cells, and it also acts as a foundational diode, creating a depletion region and it is this depletion region which allows current to flow in one direction. So for p-n junction, when they are connected in the forward bias, they will allow to flow the current in that direction, and it will block the current in the other direction, that is in the reverse bias. Okay, so as mentioned, p-n junction can be forward bias or reverse bias. So in forward bias, what happens? P-type material is connected to the positive side and n-type material is connected to the negative terminal, and the depletion layer or the depletion zone between the two types of materials, the actual p-n junction, is very small, very narrow. So it means the resistance is low. So if resistance is low, the flow of current would be higher. So in forward bias, we have p connected to positive, n connected to negative, and because of less wide or small depletion layer, the resistance is also low and current is large. Most of the carriers are in the conducting mode, okay, both electrons and holes. In reverse bias, p-type, it's connected to the negative terminal and n-type region is connected to the positive terminal, and the depletion layer between two types of regions or the p-n junction is very wide. So this is why the resistance is high and only a small amount of current is able to flow, and most of the carriers are blocked or they are not active because of a wider depletion region. So those are two types of biases often used in p-n junction. Now coming to photovoltaic effect. What is photovoltaic or PV effect? You might have heard about photoelectric effect, where like any material, it is composed of electrons, and what happens in photoelectric effect, when the energy of photons which are incident on the surface of the material, mostly metals or conductors, is very high, the electrons gets knocked off from the surface of the material. They don't stay in the material, they just leave the surface. That is called as photoelectric effect. But in photovoltaic effect, electrons don't leave the surface of the material. Okay, they absorb the energy and they get raised from valence band to conduction band, or in the semiconductors, they lead to generation of electron hole pairs, but they never leave the material. So photovoltaic effect is the phenomena by which a photovoltaic cell or a solar cell produces a voltage or electric current when exposed to light or photons. This was discovered in 1839 by Edmund Becquerel during his experiments with electrochemical wet cells. So while Becquerel was working doing his electrochemical experiments, he observed that the cell voltage, the voltage of the cell increased when the silver electrodes were exposed to sunlight, and this observation led to the discovery that light can also be converted directly into electricity. So it was during this experiment he found that photovoltaic effect is conversion of light to electricity, and this was the fundamental principle behind solar cells. You can see here in the picture, If this is the sunlight or the photons which are incident on a semiconductor material, and the electrons get excited from a lower energy level to a higher energy level, and the charge movement, the electric charge movement, when it is connected to a load by an electric wire or electric circuit, the current flows. So basically light energy is converted to electrons movement, which generates current, which generates power. Okay. So this generation of power through voltage and current using the energy of photons or light is called as photovoltaic effect. Let's look at PV cell working principle, because this is the equipment which shows us or which works on the principle of photovoltaic effect. So as you can see in the picture, there is a sun, the sunlight coming, falling incident on the solar panel, which is made of N-type material, P-type material. There is this PN junction in between. Energy of photons, okay, it's incident on these materials of N-type, and this electrons, when it absorbs the energy from photons, there is a formation of electron and hole pair, and there will be flow of electrons and flow of holes generating electric current. And if we have this panel connected with the electrical circuit, there will be the flow of electrons and holes. So what is PV cell? It is a basic unit which converts energy in sunlight or light to electrical energy using photovoltaic effect. It is composed of P-type base and N-type top layer, forming a PN junction. As you can see here, P-type material is at the bottom, that's why it's a base material. N-type material is at the top layer, and the two forms a junction. How the process, as I explained just now, the light falls on the semiconductor, and because of the energy of photons incident on the surface of panel, the electron hole pairs are generated. So that's the electron, and then there will be a hole positively charged. Then there is a junction electric field which separates these two. So this kind of field which separates electrons and holes, and they tend to move towards N side and P side respectively. So electrons, they move towards N side, that is towards the top, and holes, they will tend to move towards the P type, that is towards the bottom. And because of this movement, a potential difference is produced or a voltage is produced, and when we connect the terminals of the cell using a wire or using conducting element, conducting material, the current flows through a load. You can see it in this picture where the front contact and the back contact, they are connected to a load, and when the circuit is completed, from N type to P type there is a movement of electrons, from P type to N type there is a movement of holes. So overall there is a movement of electric current due to the generation of potential difference between the two types of materials because of the shifting of electrons towards N type material and holes towards P type material. So you see here there are front contacts or bus bars, then N type silicon and then P type silicon. In between there is a PN junction which is also known as depletion zone, and then there is a back contact. So front contact and back contact will have electrical wire circuit connection which will allow the flow of electrons and holes, and that will give us power finally to the load. And now, since PV cell is the fundamental unit, one cell typically produces 1 or 2 watts of power. Now modern cells have gone up to 10 watts, but even a 10 watt power is not enough for a practical use. We may be able to like power 1 CF, 1 LED, small bulbs or lights which are coming in 10 watt, but then if we are planning to set up a solar based installation to supply power to a house also, one solar cell won't be of any use. So how do we increase the wattage or the power capacity of these cells? So we can either connect them together. So multiple cells are electrically connected to form a PV module. Okay, and these modules are further linked to form a panel. As you can see here, numerous cells which are placed next to each other, they are connected electrically and we get a module. Those modules can be connected or linked together to form a photovoltaic panel, and then those panels can be grouped into array, into the rows and columns to reach the desired or required power capacity. It is this array or PV array which functions as the primary power source, and in a complete solar PV system which is integrated with other components, this array acts as a primary source of power which is able to capture solar energy and convert it into electricity. So, if you look at the PV cell specs, the one unit cell specs over the years, before 2010, there used to be like small format cells made by 125 mm by 125 mm, and the voltage was 0.5 to 0.54 volt and voltage is 2.5 to 3. That is the maximum voltage of single cell before 2010. In the previous decade, the standard labelings were named as M0 or M2, and the wafer size was increased to 156 mm. Voltage, it went up to 0.6 and power was between 4.5 to 5.2. So, you can see this is the most widely used cell over a long period of time, that is M0 and M2. During 2019 to 21, M6 and G1 came into picture, where the wafer size was increased further by 10 mm and they were sort of like rectangular in shape, and voltage was also raised by 0.03 volt up to 0.64 and the power was 6 to 7 watt. At present, in 2026, we have got standard level M10 PV cells coming into the market, which are of 182 mm square shaped, and they can reach voltage up to 0.7 and maximum power up to 9.5 watt. And there is another cell which is named as G12 or M12 coming into the size of 210 mm, where 10 to 12 watt is the maximum power provided by one cell. So, these are how the PV cells specifications have evolved over the years, and that was all about the basic introduction that we needed before going into the solar PV systems. So, what we learned today was the concept of energy gap or energy model, and how this energy gap, that is the forbidden energy level between valence band and conduction band, helps us to classify materials based on the value of energy gap. If it is 0 or if it is overlapping, it is called as conductor. If it is in 1 electron volt range, it is semiconductor, and if it is 5 to 10 plus electron volt, it is called as insulator. Okay. And then we looked at p-type materials, n-type materials, and how they can be combined together to form a p-n junction. So, p-type material, it is created by adding a trivalent impurity to semiconductor like silicon or germanium, and n-type material is like produced by adding pentavalent impurity like antimony, phosphorus, and when p-type material, n-type material are brought together, we get a p-n junction, and it is a foundational diode or the fundamental part of a solar cell or a PV cell. When we looked at the definition or the meaning of photovoltaic effect, like that is the conversion of light into electricity, and using solar PV cell which is composed of p-n junction, and we saw how the energy from photons of light is captured by electrons, and then they get excited and electron and hole pairs are formed, and those charge carriers tend to move towards the opposite ends, where electrons move towards n-type material, holes move towards p-type material, and then once the circuit is completed, there is a current flowing through the cell. And then we looked at different specifications of PV cell which has evolved over the years. So when it started, it used to come in the range of 1 to 2 watt, but nowadays modern cells have reached up to 10 to 12 watt per cell. And to be able to use in the real world solar PV system, we connect cells together to form module. Those modules are connected together to form panels, and then those solar PV panels are connected in rows and columns to form PV array. And it is this PV array which acts as a primary source of electricity in an entire solar PV system, because it is this array which will capture solar energy and convert that light into electricity, and then that will be sent to the other components in the entire solar PV system. So that's all for today's lecture. Thank you so much.